Yes, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the second part of the various quantum numbers, which we have described already in some of our videos. And this is going to assist us in trying to describe an orbital, of course, where we said that each orbital in an atom is going to be specified by a set of quantum numbers, which, of course, are listed as the principal quantum number, the angular quantum number, and the magnetic quantum number in that particular respect. I also mentioned the concept of an electron, which I said is also going to be described using the four quantum numbers. Now, in this case, of course, I'm just going to list them in summary now that we have discussed the various representation for n for principal quantum number, angular momentum quantum number, and then we have the magnetic quantum number given as such. Of course, we can describe an electron, as I've said, using the four quantum numbers over NL, ML, and then the spin quantum number. Now, in this particular case, we are going to look at the concept of the angular quantum number, and this is going to give us a description of a quantum number that's going to be assisting us to describe the various subshells, of course, and we can be able to pinpoint which particular subshell an electron belong. Now, this quantum number is referred to as the angular momentum quantum number. Now, of course, we are going to come across it in some of our texts referred to as the Azimuthal, I hope my pronunciation are correct, quantum number. And this is designated using this specific letter given as L. Now, in our last discussion on the concept of the principal quantum number, I mentioned that this basically is a derivation of the principal quantum number, and we are going to see some of the formula that we can use, of course, in trying to describe this specific aspect of the, of course, angular momentum quantum number. Now, of course, I've given a formula that from our last discussion on the concept of simple quantum systems. I said that we can describe the angular momentum quantum number using this principal quantum number as a multiple over the ratio over 2h over 2 pi, that's Planck's constant over 2 pi. And of course, we're going to see later as we come across this specific formula, especially in a description of various quantum number, what that specific formula represents. Now, in this case, this azimuthal quantum number was proposed by, of course, Arnold Sommerfeld. And we're going to see that the works of Arnold Sommerfeld is going to assist us in trying to describe the various shapes of orbitals or subshells that we're going to come across. And of course, we have decided that apart from it describing the shapes of orbitals. Now, I've mentioned that these various shapes of orbitals are going to be, this one is going to be, of course, spherical in shape. And then we're going to have the P, which is going to be a dumbbell. And of course, we have the D, which is going to be double dumbbell. And then, of course, the F orbital was going to be a complex one, as we had represented it in various forms in our discussion. Now, in this case, we're not going to go into details on that. But one of the aspects or one of the implications of the azimuthal quantum number is that it tells us about the various shapes of orbitals. And of course, it's going to represent the energies of the subshells in increasing form, which, of course, as I mentioned whenever we were discussing on the concept of electronic configuration, I said that this is going to be going in this specific order in terms of increasing energy of the subshells. And of course, we are going to see that the S subshell is going to have least energy as compared to the F given in that specific case, whereby this arrow is going to indicate the increasing in the value of energy. Now, this specific quantum number can be described in terms of an algebraic representation, whereby it's going to be a value of n minus 1 given as such, whereby, as I had said, the value of n is going to represent the principal shell. Now, in this case, we can just give a small, perhaps a tabular form of the derivatives of these specific values for n, L. And this is going to assist us, of course, try to understand the implication of various values for this specific number for L. So, in case we have going to have some values, 2, 3. And as we said, this is going to go on to a value of n minus 1 given as such. So in this case, we're going to see that if we have the value of the quantum number represented as 0, so this is going to imply that we're going to have a S subshell, and this is going to be P, D, and of course we're going to see that this is going to go in that specific order, and F are given as such. So as I had said, this is going to be a spherical in shape, a dumbbell, double dumbbell, and a complex one given as such. So this is going to be the implication of the angular momentum, or the azimuthal quantum number, and it's going to be representing the various orbital angular quantum numbers given in this specific order. Now we can give this orbital angular quantum number in terms of the multiple of 2 pi, and this of course is going to be the multiple on this derivation of the root of this specific value for L into L plus 1 given as such, multiplied by the h over 2. So this is going to represent what we refer to as orbital angular momentum. So I'm going to put a link of basically these specific derivations that I'm going to have given on the board. And of course, I've mentioned this one for angular momentum, which is a derivation of course, the principal quantum number, which is going to be given using this specific ratio. So basically, check our link in the description box for these two specific derivations which I've given on the board. Now, of course, we can as well represent the maximum number of electrons using this angular momentum quantum number, and that's going to be represented using this specific formula. So we're going to have the maximum, just like the principal quantum number which we had measured in our previous video. They said that of course from the principal quantum number we can describe the number of electrons in of course the maximum number of electrons of course in an orbit, which we had given for K, L, M, and N using 2 times the square of n. Now in this case, for the angular of course momentum quantum number, we can describe the maximum number of electrons in the subshell using this specific notation. So this is going to be equivalent to of course 2l plus 1. So perhaps I can just give it in an elaborate form. So this is going to be 2l plus 1 given as such. So there's a difference between the principal quantum number for representation of a maximum number of electron, of course, in what we call an orbit, which we had, of course, described using the various letters, and of course the maximum number of electrons in a subshell described using the quantum, of course, angular momentum quantum numbers using those specific designation. Now I'm not going to go into details on this, but I mentioned now in this case, of course, we're going to see that the s orbital is going to consist of a maximum of 2 electrons. The p orbital is going to consist of 6. The d orbital is going to contain 10. And of course, we're going to see the f orbital represented by 14. Now, we have said that basically for the 3 basic rules of Hund's rule, Paul's exclusion principle, and of course the Hofbauer's principle, had given us one of the conditions for the maximum number of electrons. In a sense that, of course, we have said for the s orbital, this is going to be 1 orbital, 3 orbitals, 5, and 7, and each of these orbitals is going to consist of a maximum of 2 electrons. Now, in a sense, that one is going to make sense for us in trying to describe the number of electrons in this specific subshells which I've given on the board. Now, in this case, in summary form, I've said that this specific number was described by Arnold Sommerfeld, and of course this is going to assist us in determining the number of subshells of sublevels to which an electron, of course, is going to be falling under, and of course it's going to give us different shapes of orbitals which I've mentioned for SPD and F for, of course, a spherical, a dumbbell, double dumbbell, and complex. And of course we're going to see that we can find the value of L using this specific concept of n minus 1, and that is going to give us the value of L which I've mentioned on the board. Now in our next discussion, we're going to look at the concept of the magnetic quantum number, and we're going to see the contrast between the magnetic quantum number and these 2 specific quantum numbers for principal and azimuthal, which we have discussed in these specific videos. Now this is it for now, guys. Kindly check our description boxes for various links of other videos which are going to assist us, of course, comprehend the whole aspect of the various quantum numbers for representation of orbitals and electrons. So that is it for now, guys. By God bless. We catch us in our next video.